Hi everybody, and welcome back. We are still looking at page 18 in the workbook, and what we'd like to do here is just to summarize some points that we sort of discovered in the discussion at the top of this page. Okay, so let's kind of work through this information about vectors table that we're seeing down here, just one at a time, one step at a time here. This contains some facts that are going to be useful to us for the rest of the semester. Okay, so starting with point number 1 here. So for vectors a1i plus a2j, that's a vector in two-dimensional space. And then b1i plus b2j plus b3k, that's a vector in three-dimensional space. And we'll start by just noting the way that we found the length of these vectors. We use the distance formula. Okay, so this just generalizes the technique that we used above when we calculated the length of some vectors in 2 space. Okay. And moving on to point number 2, turns out that a test for when 2 vectors are parallel is just to ask, is one of the vectors a constant scalar multiple of another one? Okay, u equals lambda of v. Okay, and if one vector is a multiple of the other, we know that they're parallel. Let's kind of sneak a peek up above at what we did just to give an example of that. So, for example, these 2 vectors, v and 2v, those are parallel because 2v is just a multiple of v. That's exactly what the definition is saying. Okay, so anytime there's a number that you can multiply one vector by, all you're doing is stretching it. You're not changing its direction. Okay? All right, and then finally, point number 3 here. There's something called a unit vector, which is really important in this course. A unit vector is just a vector that has length 1. Okay, and something that we'll want to do often is to take a vector and to turn it into a unit vector. In other words, to scale its length down or up so that its length is 1. And it turns out that a way that you can always do that is to just take the vector and divide it by its length. P over the length of p will always take your vector and either shrink or stretch it so that its new length is 1. Okay, I want to illustrate that point with a specific example here. Okay, so what if we chose, LEP, I just invented a new word. Okay, so let p be 3i minus 4j. Okay. And that's a vector that does not have length 1. You can use the distance formula up here and confirm that. To turn it into a unit vector, what we can do is the calculation that we just mentioned in 3. We'll take that vector, we'll divide it by its length. Let's do that calculation. So we're going to take the vector 3i minus 4j and divide it by its length, which is going to be 3 squared plus negative 4 squared. Okay, just using the distance formula. And continuing this calculation, square root of 3 squared plus negative 4 squared is the square root of 9 plus 16, okay, which is the square root of 25. And square root of 25 is a nice number, it's 5. So we could rewrite this as 3 over 5i minus 4 over 5j. Okay, and what turns out to be true is that this vector now has length 1 and it's parallel to the p. It has both of the properties that we want. Length 1 and parallel to p. How do we really know that it's parallel to p? Well, because all we really did was we multiplied by the constant 1 over 5. We started with 3i minus 4j. We multiplied by a fifth and got this. Okay, so that's not going to change the direction, it's parallel, and I'll leave it to you to just confirm that the length is 1. So this is a unit vector that we've created.